So Obama's talking about all of this with the global warming and that, and a lot of it's a hoax. It's a hoax. I mean, it's a money-making industry, okay? It's a hoax.
This is coal. Don't be afraid. Don't be scared.
The Treasurer knows the rule on crops.
It's coal. Those opposite have an ideological, pathological fear of coal.
Fires are a natural feature of Australia, but record heat has made them more severe than usual, something that had been predicted.
Climate scientists knew this was going to happen at some point, whether it was now or 10 years from now. We were going to get this perfect storm, and it was going to be pretty horrible.
Another day, another big global warming scare. Frankly, another big global warming con.
Australians last summer bore witness close up to what the awful force of nature is capable of delivering right now. We would not be having this summit if global political leaders had started listening to the science on climate change and acting on the advice of scientists 40, 30 or even 20 years ago.
You know, I think that the climate change science is far from settled. The fact that we've had, if anything, cooling global temperatures over the last decade, notwithstanding continued dramatic increases in carbon dioxide emissions, suggests that the role of CO2 is not nearly as clear as the climate catastrophists would suggest.
With so many divided opinions, how can we decide if climate change is real or not? Is climate change really occurring? And if so, what are the underlying causes? What does the science tell us? What is the science behind climate change? To find out if the Earth is warming, we measure the temperature and see if it has changed over time. People have been recording daytime temperatures across the globe for hundreds of years. More recently, automatic systems have replaced the manual recording that provide almost real-time monitoring of the atmosphere, properties such as air temperature, pressure, humidity and wind speed. The Earth's surface is about 2/3 water. In the past, ship crews have recorded air temperature, and since the early 2000s, a flotilla of 4,000 Argo floats have covered the ocean, providing information about ocean water and temperature. Since the 1960s, weather satellites have been used to measure the temperature at the surface of the Earth using sensitive radiometers. To compare temperature changes from place to place, scientists take the difference between the measured temperature and its long-term average. This is the temperature anomaly. When averaged across the globe, the temperature anomaly varies, as in this graph. The temperature difference is roughly constant until about 1910, after which it begins to rise. In the past 100 years, measurements show that the average global air temperature has risen by almost 1 degree Celsius. As with air temperature, sea surface temperatures have also been recorded for centuries. Measurements of the average sea surface temperature anomaly show a similar rise of about 1 degree Celsius in the last century. There are also other indicators of global temperature rise. In March 2002, a pair of satellites were launched by NASA and the German Aerospace Centre. Known as GRACE, these satellites detect changes in mass of features on the Earth's surface. On passing over the Antarctic, the satellites have detected changes over time in the mass of ice. The data show the ice is melting, as highlighted by the dark regions in this graphic. The ice loss has been verified by science expeditions to the Antarctic. Likewise, the GRACE satellites have measured significant ice loss over the Greenland ice sheets. We also find that 99% of all glaciers across the globe are in decline. The Franz Josef Glacier in the southern island of New Zealand has retreated over 2 kilometres in the last 100 years. studies of a set of reference glaciers show that the rate of melting has doubled in the past 10 years. The increased ocean temperature and the melting of polar ice sheets has caused sea levels to rise, with observations showing an average increase of 20 centimetres. It has been estimated that complete melting of the West Antarctic and Greenland ice sheets will raise the ocean levels by 12 metres or more. We see that scientific measurements show an increase in the global average air temperature of about 1 degree Celsius. They show an increase in the global average ocean temperature of about 1 degree Celsius. Observations indicate that polar ice sheets are melting, as well as 99% of all glaciers, and that the sea levels are rising, consistent with thermal expansion and the melting of ice. The experimental evidence is that our planet is warming. To investigate why our planet is warming, we need to understand the Earth's energy budget, where our energy comes from and where it goes to. Our planet orbits the Sun, a huge ball of hydrogen gas undergoing nuclear fusion, emitting enormous quantities of electromagnetic radiation and high-energy particles far into space. Some 150 million kilometres away is our planet, continually bathed in this solar energy, which adds heat to the Earth. To maintain a stable temperature, the Earth must also lose heat, and it does this by thermal radiation. To understand this process, we must learn about light. Light is a form of electromagnetic radiation. This is the same kind of radiation as the radio waves from your mobile phone or your Wi-Fi connections. It is the same kind of radiation that provides heat from a log fire or that gives you sunburn. With a diffraction grating, we can form a spectrum of colours that make up sunlight, a rainbow if you like. The spectrum is much broader than our eyes can see. Beyond the violet end is the ultraviolet. Some animals, like bees, can see ultraviolet light and use it for navigation. We can feel its effects as sunburn on our skin. Beyond the red region of the spectrum is the infrared. We can't see this either, but we can feel its effects. The heat we feel from a fire is mainly infrared radiation. The difference between all these forms of electromagnetic waves is the wavelength. This is the distance between corresponding points on the wave, such as between adjacent crests or troughs. Light towards the violet end of the spectrum has a smaller wavelength. It was discovered over a century ago that all matter radiates electromagnetic waves with distributions of wavelengths that depend on temperature. A hand, for example, placed in contact with a wall departs heat to it that radiates. We can't see this radiation with our eyes, but we can detect it using a camera sensitive to infrared radiation. The hand appears bright relative to the wall because it's much warmer and emits more radiation. We can see an imprint on the wall where the hand has warmed it on touching, because that part of the wall is now emitting more thermal radiation. The peak radiation is at a wavelength that depends on temperature. The wavelength of infrared radiation is measured in terms of millionths of a metre, or microns. A human hair has a diameter of about 50 microns. Ice at 0 degrees Celsius emits most of its radiation at a wavelength of 10 microns, or about 1/5 of the width of a human hair. A log fire at 800 degrees emits at about 3 microns, and the Sun at 5,500 degrees has its peak radiation in the visible region at about a half micron. Likewise, the Earth loses heat by thermal radiation and cools. The Earth receives heat from the Sun and loses heat by thermal radiation. It remains in thermal equilibrium when these two processes are balanced. Since our measurements have shown the Earth is warming, there must be an imbalance. Either there is more energy coming from the Sun, or the Earth is not losing as much energy as it once did. The Sun is an enormous ball of burning hydrogen undergoing nuclear fusion to form helium. The nuclear reactions emit enormous quantities of radiation and subatomic particles into space. A close-up view of the surface of the Sun provided by NASA gives an indication of the violence of this process. It is far from static, with an output that fluctuates in time. Occasionally, there is a burst of radiation that arises from instabilities within the Sun. Such outbursts are truly gigantic. We get an idea of size by comparing it with Earth at the same scale. Scientists have been measuring the solar radiation reaching the Earth for many years. The output varies with time, showing a distinct 11-year period corresponding with the sunspot cycle. The variation is about 0.1% of the total radiation and shows little or no correlation with measurements of global average temperature. The conclusion is that neither the Sun nor changes in the Earth's orbit are responsible for the warming. We are left with the conclusion that global warming is a result of the Earth not cooling fast enough. That is, something is inhibiting the thermal radiation. To understand this problem, we need to look at how radiation from the Sun reaches the surface of the Earth, and how thermal radiation from the Earth radiates back into space. And this is where the atmosphere dominates. Sunlight entering the atmosphere is partly absorbed by the atmospheric gases. Some of it reflects from the gases and clouds, and about half of it reaches the ground, where it is absorbed as heat. The rest is reflected from the ground back into space. Cooling occurs by thermal radiation at a much longer wavelength, that is emitted from the atmosphere and clouds back into space. Of the thermal radiation emitted from the ground, almost 90% is reflected by the atmosphere back onto the ground. Only about 10% escapes through the atmosphere back into space, through a region known as the atmospheric window. It is this 10% of all the thermal radiation that enables cooling of the Earth's surface, and therefore there must have been changes to the atmospheric window that have reduced the rate of cooling. We have already seen an example of the electromagnetic spectrum with the visible region that we can see. When we superimpose the absorption properties of the atmosphere onto this spectrum, we observe that most of the atmosphere is opaque, as indicated by the dark regions. This leaves three main regions or windows in the atmosphere where radiation can escape into space. These absorption bands are caused by different gases in the atmosphere. For example, oxygen absorbs light in the deep red and near-infrared regions of the spectrum. Oxygen represents about 20% of the atmosphere. A large contributor to the absorption of radiation in the atmosphere is water vapour. The amount of water vapour is highly variable on the planet, ranging from almost 0 to about 4%. The next main contributor to atmospheric absorption is carbon dioxide. The carbon dioxide represents about 0.04% of the atmosphere, or 400 parts per million. Despite its relatively low concentration, like water vapour, it has a major impact on the transmission of radiation through the atmosphere. The wavelengths radiated from an object at 21 degrees Celsius has a broad distribution that peaks around 10 microns. Water vapour has a strong influence on the transmission between about 5 and 8 microns. Carbon dioxide dominates above 12 microns. And at the peak, both water vapour and carbon dioxide have a major impact on how much thermal radiation escapes through the atmosphere. In other words, both water vapour and carbon dioxide control how quickly the Earth can cool. We have found that changes in the solar radiation are not warming the Earth, but something is affecting how quickly the Earth can cool. Both water vapour and carbon dioxide, and to a lesser extent oxygen, can have a large impact on the rate of cooling. An increase in the concentration of these gases would lead to more absorption in the atmosphere, reduce the rate of cooling, leading to higher temperatures. To investigate how these atmospheric gases have changed with time, we travelled to a remote island in the Pacific, Hawaii. On the island of Mauna Loa is the National Oceanic and Atmospheric Administration Research Station. Situated at the top of a volcano some 3 kilometres above sea level and far from major industrial cities, they have some of the cleanest air in the world. Measurements since 1990 show that the oxygen concentration is falling, and the data are consistent with similar measurements taken in Antarctica. This decrease in oxygen should cause the Earth to cool slightly by allowing more radiation to leave. Similar data for water vapour content shows it has been slowly rising over the past 50 years. We know that water vapour has a major impact on the radiation through the atmosphere. However, the water vapour content has risen less than 1% in this time. Moreover, water requires heat to evaporate. Rather than a cause of global warming, the increase of water vapour in the atmosphere is a consequence of rising temperatures. The next gas to investigate is carbon dioxide. Measurements show that carbon dioxide concentrations have risen by 16% over the past 30 years and is now at a level of 412 parts per million. This seems a significant increase and is a likely cause of global warming. It is useful to measure how carbon dioxide concentration has changed over the last 100,000 years, and to do that, we now head to the Law Dome in the Antarctic. For many thousands of years, the snow falling in this region of the Antarctic has trapped air between the snowflakes. Over time, the snow is compressed into ice, trapping the air bubbles, acting like a tiny time capsule, preserving a part of the atmosphere at the time the snow fell. For at least 40 years, scientists have been travelling to this region of the Antarctic and drilling into the ice to collect ice core samples. The deeper they drill, the further back in time they go. The ice cores contain bubbles of the atmosphere that was trapped when the ice was formed. The samples are taken back to the laboratory where the gas content is analysed. In this way, a picture is obtained of how the carbon dioxide concentration has changed over the last 80,000 years. The peaks and troughs correspond to periods of warming and cooling. The maximum concentration of carbon dioxide in this period has been 300 parts per million. When we include the data for the last 100 years, we see the concentration increases rapidly by over 30%. Comparing the change in the carbon dioxide levels with global temperature rise over the past 100 years shows they are strongly correlated. The carbon dioxide inhibits thermal radiation from leaving the Earth, reducing the rate of cooling and increasing global temperatures. Calculations of the expected temperature rise with such changes in carbon dioxide predict about a 1 degree increase, consistent with measurements. The scientific evidence is now very clear that excess carbon dioxide is causing global warming. Carbon dioxide is known to inhibit radiative cooling. The rise in global temperatures is strongly correlated with the rise in carbon dioxide levels. The increasing temperature results in more water vapour in the atmosphere that also impacts global warming. there are no other explanations that are consistent with the scientific measurements. The carbon dioxide has two main sources. Some is released by deforestation when vegetation decays and dries out. Most of it is produced by burning fossil fuels and from industrial processes such as the manufacture of concrete. The carbon dioxide is distributed across the globe into three main areas. About a quarter of the carbon dioxide is absorbed into the oceans. Another quarter is taken up by land use, as in growing plants or as compost in soils. Most of the carbon dioxide finds its way into the atmosphere. We often hear about warming of the climate, but less attention is given to warming of the oceans. Water requires 5,600 times more energy to raise its temperature compared with a similar volume of air. This means the oceans are absorbing most of the heat, and it is the ocean that has the largest impact on our climate. The rising ocean temperature is associated with greater rates of evaporation of water. Water absorbs heat when it evaporates, and it releases the heat again when it condenses. Warm air rises and cools, causing water vapour to condense. Condensing vapour releases heat, warming the air and causing it to rise. This can lead to instability in the atmosphere, as we observe in this time lapse of cumulus cloud formation. With so much more energy in the oceans, this process can drive the formation of super hurricanes. Hurricanes or tropical cyclones have become more intense and more destructive over the past few decades due to ocean warming. Rising water vapour carries air with it that alters atmospheric circulation and changes weather patterns. As an example, cold fronts from the Antarctic Ocean provide much needed rainfall for southern and eastern parts of Australia. However, ocean warming shifts the pressure system south, bringing more tropical rain and storms to the northwest, pushing the rain-bringing cold fronts further south, leaving southern Australia drier. This effect is seen in the climate records, where the amount of rain around the southern coast of Australia has lessened and that towards the northwest has increased. The shifting weather patterns has created hotter and drier weather in much of Australia, resulting in a dramatic increase in the number of days per year of extreme heat. This increase correlates with the increase in carbon dioxide in the atmosphere. With hotter and drier conditions along the eastern seaboard of Australia, there is an increased likelihood of bushfires. It was predicted as far back as 2005 that the bushfire season would be more prolonged and more intense by 2020 due to global warming. These satellite images of Australia show the smoke from the fires that devastated huge areas of forest in 2019. It has been estimated that over 1 billion animals lost their lives in this catastrophe that spread smoke around the globe. Sea level rise is another consequence of global warming, much of which is associated with melting of polar ice. It has been estimated that complete melting of the West Antarctic and Greenland ice sheets will raise sea levels by 12 metres or more. The consequence for coastal cities is enormous. As we can see for the city of Melbourne, Australia, significant flooding occurs at 4 metres sea level rise. The cost of this inundation will exceed more than $1 trillion for this city alone. The warming of the oceans is not uniform but varies depending on location and time of year. Water temperatures hotter than usual for extended periods have a devastating effect on sea life. Corals are particularly sensitive to excessive temperatures and will die, leaving the coral devoid of colour. This coral bleaching, particularly along the Great Barrier Reef along the northeast coast of Australia, has become more frequent in the past 2 decades. The dark red regions of these satellite data show where the water temperature has remained excessively high and correlate with the mass coral bleaching events of 2016, 2017 and 2020. The oceans absorb significant amounts of atmospheric gases, carbon dioxide included. When mixed with water, the carbon dioxide reacts to form carbonic acid that is making the oceans more acidic, a process called ocean acidification. Already, scientists have measured a decrease in the pH of the ocean, a measure of acidity. The lower the pH, the more acidic the solution. The pH change is not uniform over the ocean surface, which becomes more acidic as the carbon dioxide levels increase. If carbon dioxide levels continue to increase at their current rate, the pH of the oceans will reach 7.7 by the year 2100. This will have a major impact on oceanic life. The oceanic food chain depends on the presence of pteropods, small shelled creatures like these sea snails. Their shells are formed from calcium carbonate. When the ocean pH drops, the amount of calcium available for shell formation is reduced, and scientists have observed the dissolution of the pteropod shells in ocean water with a pH predicted for the year 2100. This means that a large number of shelled creatures will die, including plankton, crabs, shellfish. Since these creatures form a vital part of the oceanic food chain, their loss will impact many small and large fish species, such as salmon, as well as many other creatures such as whales and even seabirds. Ocean acidification, driven by excess atmospheric carbon dioxide, has the potential to wipe out over 50% of all ocean species, leaving 1 billion people starving who rely on the sea for their food. To avert catastrophe, we need to stop emitting carbon dioxide into the atmosphere. This means an end to burning fossil fuels. Carbon dioxide can be removed from the atmosphere by forests. We need to be planting more trees and vegetation, particularly in and around our cities. This will also help reduce heat island effects associated with overdevelopment. Fossil fuels are not renewable and will run out eventually. There is no reason we cannot transition now to renewable forms of energy such as wind power, solar energy and wave energy. As a community, we should be investing into research and development of more efficient ways of using and storing energy. Simple changes to building design to include passive heating and cooling can make a huge impact on our energy usage. There are many things we can do to improve the planet that sustains our lives. The science is very clear and has been for many years. The Earth is changing because of too much carbon dioxide in the atmosphere. The solutions already exist. It is now up to us to change our ways.